All right, in this video, we're going to look at taking derivatives in parametric form. If we want to find the first derivative for y, for instance, or the first derivative or the second derivative for y with respect to x. Now, we can think of the formula for the derivative in parametric form to be related to the chain rule. So if you recall the chain rule, we were trying to take the derivative of y with respect to t when we had a function of y with respect to x, but then x itself was a function of t. So this was sort of the traditional way of looking at the chain rule. But in this case, we have a function of y with respect to t, which we can easily find the derivative for. And we have a function of x with respect to t, which we can also easily find the derivative for. The thing that we don't have is the derivative of y with respect to x. And if we solve this equation for dy dx, then we very clearly get dy dt over dx dt. So this is the pattern that we're going to follow as we go through this example. So we're going to first find y prime, i.e. dy dt, and we're just going to take the derivative of y with respect to t. The function of y, the function y with respect to t is t cubed, so the derivative of that is 3t squared. And x prime, or dx dt, is, again, this is our function of, this is our x function with respect to t. We're going to take that derivative. We're going to get 2t. And so dy dx is going to be 3t squared divided by 2t, which we can simplify to being 3/2 t. Now, from this point, for the first derivative, we could do things like find the equation of a tangent line. Now, in this kind of context, we would have to be careful. Sometimes they will give us values for t, and then we will have to plug the values in for both x and y. I will save finding the equation of the tangent line for another video. But in this case, we also want to continue on to find the second derivative of our function. Now, the second derivative is going to start here with the first derivative, but of course, we have this, essentially this chain rule going on. Again, if I take this derivative, the derivative of y with respect to x, dy dx, and then I take the derivative with respect to that again, d over dx, then I'm going to have to, now this dy dx is itself a function of t already, and so I'm going to need to take the derivative, but then I'm also going to need to multiply it, or actually divide it in this case, by another derivative of x. So what I'm going to end up with is essentially dy dx, a function of t. I'm going to take that derivative with respect to t, and then I'm also going to divide by another derivative for x. So this will become d over dt, dy dx, divided by dx dt. That should be a t on the bottom there, sorry. So my derivative up here is going to be, the derivative of 3/2 t will just be 3/2. And then I will divide again by another 2t. And so now this will become 3 over 4t. And that will be my second derivative. Now, we could do some algebra to try to verify that some of this makes sense. And to do that, we would have to solve our expression up here for having just a function of x and y. But I will leave that for another video because you can, in fact, do the algebra to find an equation for x and y. Essentially, you have to solve for t. So we could solve for t here, plug that into here so we could get a function of x and y. And then from there, we could find our derivative for x with respect to y directly. And then we would be able to see that if we, in fact, substituted t in for wherever we had x and y, we should get this exact expression back again, so that they are, in fact, algebraically equivalent.